In this video you will learn the difference between large and small cyclone separators and why multi-cyclone systems are used in industry. In a large cyclone, the diameter is wide. While it handles huge volumes of gas, the centrifugal force at the outer edges is relatively weak. This means smaller dust particles often stay entrained, they just float along with the gas stream and escape right out the top. Only the large particles get thrown to the walls. Now, if we look at the small cyclone, as the radius is tighter, the centrifugal force is significantly higher. So it creates a high-velocity spin that flings even the tiniest dust particles out of the airstream. The disadvantage with this is that one small cyclone can't handle much flow. To get the same throughput as the big cyclone, you need a lot of pump power, which leads us to a clever engineering workaround. This is a multi-cyclone setup. Instead of one giant, inefficient cyclone, we use a battery of small-diameter cyclones working in parallel. The dirty gas enters a common manifold and splits into these individual units. The clean air exits through the top vortex finders. Meanwhile, the dust drops into a shared hopper at the bottom. The advantage of using a multi-cyclone is that if one cyclone fails or clogs, the others keep operating, so production keeps going. They are highly precise, allowing small diameter separation. To understand why this happens, let's have a look at the math. This is the formula for centrifugal force. Fc is the centrifugal force. M is the mass of your particle. V is the rotational velocity. R is the radius of the cyclone. Notice that radius is at the bottom of the fraction. This means it has an inverse relationship with force. If you increase the radius, making the cyclone wider, the centrifugal force drops. Let's look at an example. As the gas spirals, the centrifugal force pushes particles toward the outer wall. Watch the large particles, they have more mass, so they feel that force immediately and get flung to the edge with a larger radius cyclone. Once they hit the wall, friction takes over. They lose velocity, slow down, and gravity pulls them down the cone into the hopper. If you decrease the radius, the force spikes. This is more effective for small particles. When we tighten the radius and increase the force, that these tiny particles are finally flung to the edge and removed. It's a game of physics where every millimeter of the cyclone's diameter counts. Conversely, if you want more force to move those particles, you either need a heavier particle or you need to crank up the velocity. But since we can't always change the dust we're cleaning, changing the radius is our best lever for performance. If you enjoyed this video, please make sure to like, share and subscribe for more engineering videos.